Okay, so today we are going to have the third lecture where we will continue from the things that we had seen before. So let me first recall the stuff that we had seen last time. We had talked about two things, namely the row echelon form and the reduced row echelon form. And we saw things called row operations. There were three types of row operations, which we call as elementary row operations. So we had three of them. One was multiplying the row by something, the other one was swapping the rows, and the third one was trying to add a row, a multiple of one row to the other. So I'll just write them in a nutshell so that we are reminded of what it was. The third thing we had done was adding a multiple of one row to the other. So using these row operations, we claim that we can get a row echelon form of any matrix and also the reduced row echelon form of that matrix. Now, one thing which I would like to remind, and if we see in the previous example that we did last time, the row echelon form is not unique. In fact, a matrix can have infinitely many row echelon forms. But when it comes to reduced row echelon forms, that is always a unique form. So in some sense, the importance of reduced row echelon form also lies in the fact that it is the only form for a given matrix. So that anybody who does reduced row echelon form should end up getting the same matrix. One more thing I had done last time, so let me recall that for you. I'd use this abbreviation RREF to refer to the reduced row echelon form. Okay, so I pick up from the example that we had seen last time. We were trying to deal with this system of equations. X plus 3y equal to 4 and 5x minus 4y equals minus 7. And we wanted to find the solution using the ideas of echelon forms. So we said, let's create the augmented matrix 1, 5, 3 minus 4, 4 and minus 7. And we will try to get its echelon form. And well, we'll try to get the reduced row echelon form as well. So the idea of echelon form and reduced row echelon form was that we wanted to produce, let us say we want the reduced row echelon form. We want to produce ones, as many ones we can produce in a column. Or it may happen something like this, 1, 0, 0, 0, 1, in which case this should become 0. So one of these guys is what we are aiming for. And as you can see, both of them are reduced row echelon form or possible reduced echelon forms of this matrix. It may happen that we end up with this, it may happen that we end up with this, and based on what we end up with, we can tell you something about the solution for this system of equations. Okay, so let's try and see how things go. Since we want to create ones and zeros, so we will try to use row operations. We already have a 1 over here, so that's nice. We use this entry to try to take this entry out. And to do that, we'll use a row operation, which says minus 5 times row 1 added to row 2. Now remember, whichever row we are using as a multiplier row will remain unchanged. And the action is done on the row which is our target. So this would be 0. This would be minus 15, minus 4 gives you minus 19. And this is minus 20 and minus 7. So this should give you minus 27. Now let us ask ourselves a question. Is this an echelon form for my matrix which is written over here? And the answer to that is yes. If you recall echelon forms, all 0 rows should be at the bottom. We don't have a 0 row. and all the leading entries or leading non-zero entries should have zeros underneath them. So this is a leading entry, this is a leading entry, and as you can see, they do satisfy the definition of echelon form. So this is a possible echelon form. Let's see if we can get something out of it. Of course, we can solve the system from here itself, but we'll try to do and see if we can go for the row reduced echelon form. Now let us say if I want to go for the row reduced echelon form. Remember, this is echelon. If I want to go for the row reduced echelon form, I need to make this guy 1. So for that I'll use another row operation. I will multiply the entire second row by -1/19 so that I can get this as 1. So this is 1, 3, 4, 0, 1, 27/19. And this is what we are getting. Now if you notice, these have got this new form, which is again an echelon form. So it kind of corroborates what we had mentioned over here, that the echelon form need not be unique. And right now we have 2 echelon forms. Both of them are good, equally good. But suppose I want to go from here to the row reduced echelon form, then I should use this entry to try to make this entry, the one above it, 0. Because in the row reduced echelon form, the leading non-zero entry should be the only non-zero entry in its column. So if I want to do that, I will say -3 times row 2 added to row 1. And let's see what the effect of that is. So this will give us 1, but let's first write this guy out. Okay, so -3 times 0 added to 1 will give you 1. -3 plus 3 is 0. And -3 when added to, when multiplied to this and added to 4, well, let's see, it will give you -81/19 plus 4. Okay, so it will give you -5/19. Okay, now if we come here, can we say this is a row reduced echelon form? It is indeed a row reduced echelon form because each of the leading non-zero entry in its row has become 1, and that is the only non-zero entry in that particular column. So these are our leading entries here. These were the leading entries over here. These were the leading entries over here. So leading entries will play a significant role later on when we talk more about these kind of systems. But right now let us see what have we achieved. We say that this row reduced echelon form will help us find me the solutions to this system fairly easily. And let us see the reason why. Because if you look at it, if I convert it into the system of equations, so I'm going to convert to the system again. How does the system look like? This will be x times 0 plus 0y equal to -5/19. So if I ignore the 0y, so can I say x is -5/19, and likewise in the second column, y will be 27/19. So if you look at the row reduced echelon form, it pretty much gives me the solution right away without doing anything else. I can simply read out the solutions using this form, and that is the convenience we are after, that given any system, can I somehow reduce it to its row reduced echelon form, and once I have that, I can talk about its solutions. Now, let me introduce a terminology which I had mentioned last time also. Let's talk about 2 things. One of them is the idea of a pivot entry, and then we will talk about non-pivot entries. Okay. Of course, anything which is not pivot will qualify as non-pivot. So non-pivot is not something very significant for us in terms of non-pivot entries. But what is a pivot entry? Pivot entry for us would be the same as the leading non-zero entry. In echelon form. Okay. And as we shall see, that it will correspond to the leading non-zero entries of the row-reduced echelon forms also. So for example, these guys, or these guys, or these guys are all pivots. And we would be interested in knowing the pivot entries for a reason that will be clear a little later. Now, since while we are at it, let's see what non-pivots are. Of course, any entry which is not a pivot entry is a non-pivot entry. Nothing is of significance there. But we would be interested in something called a pivot column. Sometimes they are also referred to as the basic columns. So pivot columns will be the ones which contain the pivot entry. So we will say columns with pivot entry. And just like pivot columns, we will also talk about things called free columns. These would be the columns which do not have a pivot entry. Okay, so let's first see how is this going to be applied in our present example. The first column out here will be a pivot column. Because it has a pivot entry. Likewise, the second column is also pivot column. And this column, which does not have a pivot, will be called the free column. It's just that even though these definitions are fairly obvious, but it will just help us say things in a better way. And that is why we are having these kind of names given to certain things. Okay. Now, let me also introduce two other things. Again, we use the same terminology of pivots. Just like pivot columns and free columns, we will talk about two types of variables. Pivot variables and free variables. So what would be pivot variables? Well, variables which correspond to the pivot column. Erase this part from here. Variables corresponding to pivot columns. And what will be free variables? Variables corresponding to the free columns or the non-pivot columns. Now I'm going to make a very obvious statement right now, but the obvious statement will later on turn out to be something of a very significant value to us. What I'm going to say is as follows. If I take all my pivot variables and if I take all my free variables, add them together, then that will give me the total number of variables. Now it's a very obvious statement, but later on we'll see it will be linked to one of the most important theorems of linear algebra, and that theorem will be called the rank nullity theorem. So somehow this simple statement converts into a very nice theorem. So we'll keep in mind, later on we shall see how all these things get tied up. Okay. So out here if you look at it, we have two pivot columns, and since these columns correspond to variables, so the variable corresponding to the first column, which is our x, would be the pivot variable. Likewise, this is a pivot column, so the variable corresponding to the second pivot column is y. So y is also a pivot variable. In our case, there are no free variables. Remember, this third column is not a variable column, it was the right hand side of my equation. So that is a non-variable column, so that is not what we want to include as the free variable because it doesn't correspond to any variable whatsoever. Okay. Now with this terminology, let us first try to understand, is there a way for us to predict how many solutions will a system have? Okay, so let's try and do that and see how these things can help us. Suppose I had a system of equation. I start with some system. And let us say I got its row reduced echelon form, which looked like this. So I started with some augmented matrix, and this is what it looked like. Say 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 1. Let us say, suppose I got something like this. First of all, can we say that it is a row reduced echelon form? You can check it matches the definition of row reduced echelon form. We have ones as the leading non-zero entries, and everything else is 0 in that column. So what are the pivots? So pivots in this case are 1 and 1, basically this one and this one. What are the pivot columns? Pivot columns are the first column and the third column. Okay. So this is my first column, second column, third column, fourth column. So that is why the pivot columns are first and third column. What are the free columns? Free columns are the non-pivot columns, so the second column. And if you want to call this as the fourth column, so the fourth column are the free columns. Now what about the pivot variables? What would be pivot variables? The variables corresponding to the first column. So suppose the variable corresponding to the first column was x, this was y, this was z. So we will say that x and z are pivot variables. And when it comes to the free variables, y is the free variable corresponding to this guy, which does not have a pivot. Let me repeat this. The right-hand side column, since it is not corresponding to any variable, so even though it is a free column, but we don't say this will give me a free variable. This is a very common mistake, so we should keep that in mind. Now once this is clear to us, let us see what would be the system of equations which would correspond to this row reduced echelon form. So whatever system I started with, it gave me this row reduced echelon form. So this will tell me x is equal to 2. The second equation will be what? 0 is equal to 3. Actually, let me change this for a moment. Let me call this as, we have a problem. Actually, in this example, I made an error. Okay, let's see. Let's learn from the error that I have made. I didn't realize, but it's a good learning point. Question is it a row reduced echelon form? The answer to that is no, because this thing is the leading non-zero entry in its row, and because of which this will not qualify as a row reduced echelon form the way it is written right now. So we'll have to make some changes. So if I want to make it row reduced echelon form, we will have to do some swapping. So we will swap row 2 with row 3 and see what will happen. 1, 0, 0, 2, 0, 0, 1, 1, 0, 0, 0, 3. Okay, now we are in business. And let's see, because of which, what things will change. Okay, let's try it again. So this is an echelon form. this is not row-reduced echelon form. And the reason for that is because we have 3 as a pivot entry. But let us work through this again so that we can understand what things have to be changed. Pivots. So what are the pivots in this case? This entry out here is a pivot, this entry out here is a pivot, and this entry out here is a pivot. So it is 1, 1, and 3, which we have the pivots. What are the pivot columns? The first column is the pivot column, the third column is the pivot column, and the fourth column is the pivot column. So first, third, and fourth. What are the non-pivot columns? Only the second column, which is the remaining guy, is the free column. What are the pivot variables? Variable corresponding to this guy, or the first column would be pivot variable. So x and z still remain as pivot variable, and free variables will correspond to the second column. So y still remains as our free variable. Okay. Now, in fact, it turns out to be something very nice that I made this error, and this error will turn out to be instructive for us for a totally different reason. Let's see why. Even though this is not row-reduced echelon form, but as long as it is echelon form, this is still going to be useful. So what we will do is we'll take this form, convert it to system of equations, and see what it gives us. So can I say the first equation tells me x must be equal to 2? Can I say the second equation tells me that z must be equal to 1? And can I say the third equation tells me that 0 must be equal to 3? So if you look at this system of equation that I started with, I ended up here. It says x must be 2, z is 1, y is anything. That is why you can say y is free, and hence the name free variable. But the problem is this last equation. It gives us something which is very unsettling. 0 is equal to 3. What does this tell you about the system? It says x is 2, z is 1, y is arbitrary, but 0 equal to 3 kind of ruins the whole thing. And this tells me that this system, whatever that might have been, this system has no solution. Remember, we had used a terminology, inconsistent system of equations. So if we were to take a guess, looking at the echelon form, is it possible for us to predict when will the system have no solution? Then if you look at this example, the reason we did not have any solution is because the pivot entered this right-hand side column. And whenever that will happen, the pivot is in the right-hand side column of the augmented matrix. Can we say that a situation like this will bound to occur? 0 is equal to 3 is bound to occur. 3 not particularly 3. But whatever this pivot entry is, it will be non-zero. So this will give me 0 is equal to non-zero. And that will tell us that the system is inconsistent. So let us note down this observation. So the observation we made was, suppose I have a system of equation whose augmented matrix looks like this. So A is the coefficient matrix, B is the right-hand side vector. And let us say, if I row reduce it to say R, C, where R is the echelon or the row reduced echelon form of A. Vector B gets reduced to vector C. Then the observation we made was as follows. and we can say the right hand side column of the reduced augmented matrix has a pivot, then the system is inconsistent. Notice that it really doesn't matter what kind of columns I have, as long as this guy has a pivot in it, it will always tell me that the system is inconsistent. Now, with more observations, we'll try to, with more examples, we'll try to add points to our observations and see if we can predict somehow things even before row reducing it. Can we say something about the solutions or the system being consistent or inconsistent? Let me ask you a different question here. We said, if this happens, the system will be inconsistent. What about the converse of this statement? Will that be true? That means, can I say every inconsistent system, when row reduced, will have this problem, or will have this property that the pivot will enter the right hand side column? So this is a question we would be interested in, and you should think about it. So the question we are asking is the converse also true? That every inconsistent system, the inconsistency will only come in this way and nothing else. So let's try another system and see what all other observations can I make. It seems that pivots and free variables are controlling the whole show. So how about something like this? Suppose I got the echelon form of some matrix as this. Say 1, 2, 3, 4, 0, 0, 0, 2, 1, 2, 0, 0, 0, and say, let's make this guy 7, and let's make this guy 5. What about a system which looks like this? Well, let's see. I'm deliberately writing things which are in echelon form so that our main focus should be that how can echelon form help us out. So if we go for the pivot columns, let's see what happens. The first column is a pivot column because it has 1 as its pivot entry. The second column is not a pivot column because it doesn't have pivot entry. The third column has a pivot column, is a pivot column because it has the pivot entry 2. The fourth column has a pivot because it has entry 7. This is not a pivot column, the right hand side column or the fifth column, because 5 is not a pivot. Okay. So what we see is that every row has a pivot, and all the pivots are with the coefficient matrix, and nothing is there in the right hand side. So can we say that the system will be consistent? So remember, we are trying to see whether the converse is true or not. If the converse is true, then that would straightforwardly tell us that the system is consistent. But let us see why. Okay, these are our pivot columns. So if I want to say free columns would be the second column and the fifth column. What are my pivot variables? Corresponding to the first column, let us say the variable was x. Second column is a free column. Third column, let us say x, y, z. So third column is z column. The fourth column, let us use the letter w. So pivot variables are x, z, and w. And what were the free variables? Free variable is corresponding to the second column, and we said y was associated with that. So let's call y as our free variable. So let's see if we can understand this. And is the system consistent or is it not consistent? Let us see if we convert this guy into the system of equations. Can we say x plus 2y plus 3z plus 4w is equal to 0? And then we have 2z plus w is 2. and then we have 7w is 5. Now, remember, we have said something about pivot variables and free variables. What about the rest of it? Can I find the value of w from here? Well, if I divide by 7, I'll get w. Once I have my w, can I come back here and plug it in to get the value of z? So once I have my w, I will be able to get the value of z. Once I have both z and w, would you agree w and z can be plugged in here, and this will give me the value for x. But what about y? Didn't we say y is free? That means y can take any value it wants. So let us again repeat the story. I can get w, I can get z. Once I have both w and z, then what we are saying is no matter what y you pick, you will be able to get a value of x. So we agree that is always possible. Then that means the system must be consistent. Because then we are saying, oh well, we can always find values x, y, z, and w for which this has a solution. So let's try it. Let's try to do it nicely. So w turns out to be 5/7 from here. Then z turns out to be 2 minus 2w. Oh, I'm sorry. 2 minus w over 2, which would be 2 minus 5/7 over 2. And that will give us 9/14. So I have my w, I have my z, and let us see what x looks like. X would be minus 2y minus 3z minus 4w. So this will look like minus 2y. Right now we are not giving any value to y so far. So let's play as long as we can. 27/14, and this is 20/7. So this will all look like 14, and this will be 47/14. Okay. Now, we were saying, once I have my z, once I have my w, then I can always pick a value of y, and for every value of y, I will be able to get x. So if I pick, say, y is equal to 0, my x is minus 47/14. If I pick y is equal to 1, I can compute it, and it will turn out to be minus 75/14. So in some sense, what are we claiming? How many solutions does it have? Since for every y, we pick, every real number y we pick, there is an x corresponding to it. So we will say the system is consistent. In fact, we can say much more than that. Not only we can say the system is consistent, it will have infinitely many solutions. So that is the beauty of the whole thing, that we are telling a couple of things together. Not only we are saying it has a solution, we are also telling it has infinitely many solutions. So let us see, why did this infinitely many solutions come into existence? Because I can have infinitely many choices for y, so I can have infinitely many choices for x based on the choice of y. So we have infinitely many solutions. Actually, if you observe, y was a free variable. So this tells us that if in my system I can have a variable which is free, then it can open the door for us to have infinitely many solutions. Now, why am I saying it opens the door? Why am I not just saying it will have infinitely many solutions? If you look at the previous example that we did, we did have a free variable, but still we did not have any solution. So having a free variable is no guarantee that I will have infinitely many solutions. However, if the system is consistent and it has a free variable, then we can say it will definitely have infinitely many solutions. So this is also one of the observations that we will have it over here. for a consistent system, having a free variable means it will have infinitely many solutions. So, suppose we combine this observation with the observation we made a little while ago. Can I say, if I have at least one free variable and the pivot does not lie in the right hand side column, then the system will always have infinitely many solutions. So can you say that? If you think this statement would be true, and this kind of tells me that how we were able to get this. Because if I don't have a pivot in here, then that means I'm guaranteed I have a consistent system. And in which case, that statement follows fairly easily. So now the question is, when can we say the system will have unique solution? So somehow the presence of free variable was the one responsible for infinitely many solutions. So if most likely, what we can predict at this moment is, if I don't have any free variables, then hopefully then we can talk about unique solutions. So the question is, if I don't have free variable, is it a guarantee that it will have a unique solution? Or does it depend on something more than that? We'll see that in a moment, but let me first wind up this example with one more thing. We want to learn how to write solutions to these kind of systems. Okay. We have solved everything, but we want to write it in a more pleasant way if possible. So we will choose the so-called vector form to write our solutions, x, y, z, w. Okay, and see how it turns out to be so nice for us. Remember we said w is 5/7, so this is 5/7. Z is 9/14, so this is 9/14. Y is free, so we'll just let it be y. And x is minus 2y minus 47/14. So we will always try to write the solution set in this form. And since y is free, we should also indicate that what are the choices for y. Y could be any real number I want. In fact, let me write it in a slightly different manner. I want to separate things that contain y and the ones which do not contain y. So for example, can I split this as follows? 0, 9/14, 5/7, plus y times minus 2, 1, 0, 0. One may ask, why am I writing the solution in this way? Again, we will later on see the significance of this kind of a split, but at least right now I can give you a geometrical description. What this solution is telling me is that if I plot this in 4 dimensions, this solution would be actually a line. So it will be a line in 4 dimensions. So you'll say, oh, well, that is not very helpful. What kind of a line are we talking about? Remember, when we are in 2 dimensions, I can tell you about a line if I know a point on the line. So suppose I give you a line in 2 dimensions. All I need to tell you is a point on the line. Any point is good. And as long as I can tell you the vector which lies along that line, then would you agree I have given you the complete line? Once I have a particular point on the line and a way to move along the line. So, this is the point we will say is my particular point. This is the particular point on the line. And this is what we say as a vector along the line. So I know a point on the line and I know a vector along the line which will help me travel on the line. Now, those of you who might have taken differential equations, you might have heard of a phrase, some terminology called a particular solution and a homogeneous solution. This is what we call as a particular solution, and this vector along which we are trying to move will be called the homogeneous solution.